Let's go back to beginning of the semester. And we talked about mixtures, right? I think we talked about mixtures then. Or was that in this? Let's see. I can't remember. Let me look. Structure. Have we? Oh, we haven't talked about mixtures yet, have we? Have we not talked about mixtures? No. Okay, well, we better define a mixture. In order to have a mixture, you have to have two or more pure substances first. Now, pure substance can be an element, nothing but that element, like gold. Or it can be a compound, like water. Like pure water, distilled water would be a pure substance. In our case, we have two pure substances. One is sodium chloride, compound sodium chloride, and silicon dioxide, or essentially sand. Those are pure substances. We mix them together. Do they change their identities? The answer is no. Mixtures do not alter the identity of the components that are the pure substances that are put together. So they still retain their identity. The sand and the salt, in our case, are still as is. They're just blended together. Now, if you have some type of mixture where the percentage composition of each of the substances is the same throughout, right? Any place you sample, you're going to get exactly the same composition. Then that's a homogeneous mixture. If they're allowed to settle, such as a mixture of, sand and water, right? Mix it up real good and you think you got it mixed, you wait just a few seconds after you stop stirring it and it settles out. You have a heterogeneous mixture because the composition is different wherever you look in that mixture. This sand and salt mixture is essentially heterogeneous, but I try to make it as homogeneous as possible so when I sample it that I'll get a representative sample. And I've got 6 little cups up here. You only need to take one and note the number on it. When you acquire one of those, write the number in your data page. Code number on your data sheet. Code number. That's what goes there. That way, I'll know what how much you're starting with, roughly, because I've got the masses of each one of those written down. Okay, so how do you separate a mixture? Do you need physical means or chemical means? If the identities are still the same, we can separate them by physical means. Right? So, in our case, physical means are in terms of solubility. If we add some water to our mixture, which component is it going to dissolve? Just the salt, sodium chloride. It won't dissolve the sand. So when you mix it up and you filter it, then that filtration removes the sand from the mixture. And the sand is retained in the filter paper. Okay? The solution that goes through contains the salt. So how do you recover the salt from that new mixture of water and salt? You evaporate it, right? You take that beaker, which you have weighed already, and it's collected the solution that came through the filter, put it on a hot plate, and evaporate all the water. Then when you weigh it again, you subtract the weight of the beaker, and what's left is the salt. That's the mass of your salt. Okay? How about the sand? The sand got wet, didn't it? Okay, so it's in the filter paper. So you put the filter paper on a watch glass over this boiling water bath, and it supplies heat. And that heat is sufficient to dry the paper and the sand eventually. And once you get it dried, then you can take the filter paper, and which has been weighed already, right? That's known as the tare, T-A-R-E. That's your tare weight or your container weight. You weigh it first before you even use it to filter. Then, once you've got it dried with your sand in it, weigh it again. Subtract the weight of the paper from the dried total, and you get the weight of the sand. So now you have the weight of the salt and the weight of the sand, and you can compare that percentage to, well, I have to give you the comparison. But how do you get the percentage composition? You've recovered sodium chloride, say. You started off with a mass of the mixture. So sodium chloride, the mass of your sodium chloride, and the mass of your mixture is your ratio times 100. And that would be percent sodium chloride. Okay. Now how do you get the mass of the mixture? You take that little cup and you weigh it. That's your total weight. Then you dump that into your mixing container, which doesn't have to be pre-weighed, and you add your water to it. So you take the cup and you weigh it again. And the difference between the weight of the cup now and the weight before is how much you added to the container for extraction. Okay, that's where you get this weight. Now when you get the weight for your sand, grams of sand, or silicon dioxide, divided by this weight of the mixture, that's percent silicon dioxide. Okay? You're also going to have to add these two together right here. Add these two together and you're going to get a total after extraction. You compare that value to this value and it should be less. Right? If it's completely dry, this will be less because you lost some in the extraction somehow. What would be a good reason if this value is greater than that value? If you add these two together, theoretically it should be exactly the same, shouldn't it? You just separated them physically. But experimental error is going to be slightly different. If this value is greater than that value, what's the most likely culprit? No ideas? They were wet, weren't they? And you tried to dry them? Yeah.
Not fully dry.
Right. Water. So if you've got water in here, in addition to the sodium chloride and the sand, it's going to be a greater weight than that. Okay. So that's an explanation in as succinct as I can make it. Now, particulars. Let's see, we didn't go over the pre-lab questions. Do we need to do that? Or you've already done the pre-lab questions, right? No, I did. No, you haven't done the pre-labs. No pre-labs? Okay. about number 1? Oh, read an authoritative source for a discussion of filtration. So I believe I'm probably safe in assuming that nobody's read an authoritative source on filtration. What's the basic principle behind filtration? Particle size. If you have a filter of some kind, all right, let's see, this is paper. It's in your funnel. So there's your filter paper. And we put something in it. The pore size on the filter paper is, say, 1/10 of a millimeter. Let's make it better. Let's say the pore size is 0.01 millimeters. Okay? Now, if you put something in there where the particle size in the mixture is 0.001 millimeters, and there's something mixed into it that's maybe 0.1 millimeters, will that separate them? Yeah. These are going to go through the filter. These are going to get retained by the filter because that's the pore size. These are bigger than the pore size, so they won't go through. These are smaller than the pore size, so they'll go through. That's the principle behind filtration. You separate based upon particle size and the pore size of your filter. All right. So, how about 2? What safety precautions should be taken when evaporating the filtrate containing sodium chloride?
Wear an eye protection.
I'm sorry?
Wear eye protection.
Eye protection? Okay. Watch out for your eyes.
Be cautious of splattering.
Splattering, yeah. So you need to heat it. You can heat it fast in the beginning because most of it's water and you're going to boil the water off. But as you get lower and lower and lower in water, you're going to develop hot spots. And those hot spots, which are typically due to accumulations of granules of the solid, will cause the water to instantaneously vaporize, and that spatters. Okay, so as you get down lower and lower in volume with the one that's got salt in it, you want to reduce the heat. Okay. What else? Well, obviously, heat in what form? Hot plate. You got a steam bath, right? So steam is going to be a hazard. And just wear your appropriate PPE. Personal protection equipment. Okay? Oh. How about 3? Define the following terms as they apply to this experiment. A homogeneous, I've mentioned this one already. A homogeneous mixture. It's a combination of 2 or more pure substances. That's the mixture part. And the composition is uniform throughout the mixture. We got another name for this also. It's called a solution. Now we normally think of solutions as some solid dissolved in liquid, like salt water, sugar water, but solutions come in all sizes, all phases. An alloy of two metals is a solution of the two metals. Okay, so that was part 1. Part 2. What do we mean by evaporation?
Process in which a solution is heated to remove the solvent.
Yep. And with reference to our procedure, remember that says, define the following terms as they apply to this experiment. We're converting a liquid to a gas by the addition of heat to remove the liquid. Okay, in this case, water. Now, there are other ways to remove liquids. Right? All you have to do is convert them to a vapor. Go from a liquid to a vapor. That's evaporation. In our case, we're just going to add heat because there's nothing in there that's going to change its identity with heat. But if you have a situation where you've got some particularly labile substances in your mixture and you want to gently remove the liquid, then you can reduce the vapor pressure above the liquid. Just pull a vacuum on it, and that will reduce its boiling point. Right? It's just like what temperature does water boil at the top of Mount Everest? About 85 degrees Celsius. Right? So the lower the pressure, the lower the boiling point. So if you continue to lower the pressure, you can remove the liquid at a lower and lower temperature. And that's one of the main ideas behind, actually it's not liquid to vapor, it's solid to vapor. We sublimate ice from a mixture by putting it in a vacuum and applying gentle heat. That's called lyophilization. And it's very, very gentle on the components of your mixture. Anyway, so that answers evaporation. How about residue? What is residue? After you finish evaporating, it's what's left over. Or when you filter something, what's caught in the filter is a residue. Two possibilities there. All right. And the last one I think is number 4. This one has several steps to it. Actually, several questions. So let's gather information. A student was asked to determine the percentage of each component in a mixture of sodium nitrate and calcium carbonate. The mass of the sample used was 2.21 grams. So, sample mass is 2.21 grams. Okay? The student extracted the sodium nitrate from the mixture with water because calcium carbonate is insoluble. That's the only way you can do that. Sodium nitrate is completely soluble, calcium carbonate is not. And then the mixture was filtered to remove the calcium carbonate from the solution. And after evaporating the filtrate is what went through the filter. It's the liquid in the bottom. The student recovered and dried the sodium nitrate in the filtrate and found that it weighed 0.43 grams. So the sodium nitrate recovered weighed 0.43 grams. And the residue in the filter paper, calcium carbonate, recovered And these are results after we weigh the container with the compound and subtract the weight of the container. Right? This has already been done. Is 1.67 grams. Okay, that's everything that we're given. Now the questions. So 1A says, calculate the percent sodium nitrate in the mixture. How do you do that? There's the mass of the sodium nitrate, and there's the mass of the mixture. Right? You get a value. So how many, two significant figures? Anybody do that one yet?
.19.
Did you multiply it by 100 yet?
Nope.
That means percent.
19%.
Yep. Okay. B question. Percent calcium carbonate. So that's this one divided by the total times 100. And this one can have three significant figures.
.76.
Mm-hmm. And this is mass. Okay, 2. Calculate the total mass of sodium nitrate and calcium carbonate recovered. So here all we have to do is add these two together. Plus 1.67. Well, let's see. If we use our rules for significant figures, we ought to line up the decimals. 0.43 and 1.67. 2.10, right? We can keep that last one. That's the total. 3. Calculate the percent recovery of the components using the total mass of the substances. Okay, so this is what was recovered. That's what we started with. So what's the percent recovery?
Subtract them and count 100.
No, percent recovery. How much was recovered in a percentage basis? See, that was recovered from that starting amount. So the percent recovery is this ratio to that. Right? But this value ratio to that starting value.
95%.
95.0?
Yeah.
That's not bad. We only lost 5% in the process. Now the value that you would have calculated would be the 5% if you took the difference and ratioed it. And calculate the percent error for the separation. That's actually what we're doing with this one. 100 minus 95 equals 5% error. Because we lost that much in the process. Okay? So you should be able to do the calculations once you get your data, because it's based upon these same calculations.